Welcome back. So as discussed in the previous video, we have seen the theoretical concepts of curl, a wonderful tool of vector calculus applied to the electromagnetics. We have also seen one of the example numerical and solved it. And in the previous slide videos, there were two numericals that were given as a homework. Today, let us discuss the solutions of those two numericals. Moving on to the first one, evaluate the closed line integral of h about rectangular path, the 4 points that are given here, and the value of vector field h is also given in the form of an equation. This is the first part of the numerical what is required to solve by traditional line integral method, that is integral of h dot dl is equal to I. The second part of the numerical is to determine the quotient of the closed line integral and the area enclosed. So what we are doing here is as an approximation of curl of h. So what we do is integral of h dl is found in the first part. We divide it by the area that is enclosed by those 4 points, which is by default the approximate definition of the curl, not the exact definition, because if it is an exact definition, we are supposed to apply the limits. Thirdly, we are determining the curl at the center by using the determinant method or by the available formula. So if we have understood the statement of the numerical, let us break down into 3 parts and follow with the solution. So moving on to the solution of the first part of the numerical, that is to find the closed integral h dot dl. So let us try to visualize those 4 points in the Cartesian coordinate system. The axes are shown, x, y, z axes are shown here. So this will be the line joining P1 to P2, where the coordinates are 2, 3, 4, that is x value 2, y value 3 and z value 4, and point to only the x coordinate changes, y and z value remains same. So the point P1 to P2 direction is in positive x. Secondly, we have to plot a path from the points P2 to P3. So that is, see here, x and y coordinates are same, z value reduces by 3. Z was 4 at P2, at P3 z becomes 1, which means the path is downwards. And similarly, P3 to P4, we see that x value goes back by 2, whereas y and z points remain same. So which means we are going back in the positive negative x-axis and back to P1, which was our starting point. This completes a rectangle. Now we are supposed to evaluate the line integral h dl for this particular rectangle with the given points. Let us do it one by one. So what is dl vector for points P1 to P2? Now the direction for P1 to P2 is in x direction. We know that vector dl is given by dx ax plus dy ay plus dz az. But clearly, as indicated in the diagram, P1 to P2 is only in the x direction. So we can write dl as dx ax only. Now that we know what is dl, let us try to find out what is h dot dl. Now since the h equation is given here, which contains a hx term, which is 3z, and also contains hz term, which is 2x cube. Hy term is not present. Now the direction is shown here. Now the magnetic field will be in the x direction only. So of the h vector, we have to take only the hx component, which is 3z. Now where are we finding this hx component? It is in this line. In this line, y and z values are same, only the x value is changing. So at P1 and at P2, the z value is 4. So we substitute the value 4 and the equation hx will be 12. Equation hx will be 12 in the given form. So now that I want to find h dot dl, vector h will be 12 ax and vector dl will be dx ax, and it is a dot product. So we understand that dot product of ax dot ax will be 1. So in the integral we get a scalar term 12 dx. So this is the integral. Now since this is hx, we have to evaluate with respect to x from where to where. P1 to P2 is the integral we are finding out. In P1 x is 2 and in P2 x value is 4. Our path is from P1 to P2. So the limits of the integral will be 2 to 4 as shown. The integration of 12 dx with respect to x will be 12x with the limits substituted. This is the solution. So from the path P1 to P2, line integral h dot dl, which is equal to I, is given by 24. Now similarly, we have to find this h dot dl for P2 to P3, P3 to P4 and P4 back to P1. So this is to be found out. So once we find this, we have to add everything. Then we will get the total h dot dl, which is asked here. Evaluate the closed line integral of h. So if the step discussed here is clearly understood, we can proceed with the next part. That is to find the line integral from P2 to P3. Let us give 5 seconds time to understand this particular concept properly. So moving forward, now that we have found out the line integral P1 to P2, let us find out the line integral P2 to P3. Now the path from P2 to P3, let us slightly increase our speed because we are repeating the mathematical step here. The path from P2 to P3 here is in the reverse z direction. But for line integral, we take it as dz, az only without considering the sign, because the sign component will be considered in h. So this is in the az vector. So dz, az only. We don't have to consider dx and dy here, because for P2 to P3, dl is clearly in the z direction. Now what happens to the h? Now it is true that h in this line will be only the hz component. The question is, do we have hz component? Yes, we do. We have a x component, we have a z component. So this minus 2x cube will be hz. So hz will be minus 2x cube. Now what is the value of x? We have to substitute. We clearly see that while moving from P2 to P3, the x value remains same, which is 4. So that is the 4 value we have to substitute, but we have to do x cube. So it will be 4 into 4 into 4, 64 times 2, which is 28 with the minus sign. So this is the h value. Now that we know the h value, we apply h dot dl for the dz, which means the variable is z, while moving from P2 to P3. Understand clearly, the path is from P2 to P3. The limits are z is equal to 4 to z is equal to 1. So the lower limit will be z is equal to 4 and upper limit will be z is equal to 1. Substituting this, integrating, we get the answer as 384. You can pause the video here and rework it in your calculator just to verify whether the answer is correct. Moving forward, we have to find the line integral now for the third line, that is P3 to P4, where once again it is in the x direction and only the hx component we have to consider, which is 3z, but the z value now for the points P3 to P4 is 1. So we substitute that value and we get it. So the closed integral will be as shown in the screen. So I suggest you people to pause the video and rework it in your calculators and get the answer. Lastly, P4 to P1 is in the z direction, and we have a z component here which is minus 2x cube. We substitute it, and the z value for x value for P4 to P1 is 2. So we substitute that and we get minus 16 as the answer. Now that we have evaluated the line integrals for P1 to P2, P2 to P3, P3 to P4 and P4 back to P1, we have to add all this together in order to find the total HDL. So which will be, so P1 to P2 is 24, P2 to P3 is 384, P3 to P4 is minus 6 and P4 to P1 is minus 48. Add it together. Let us remember H dot dl is what we are trying to mathematically find out, but physically we know that as per Ampere circuital law it is I, which is current. So the answer for this is 354 and the units will be amperes because the unit for current is amperes. This is about the first part of the numerical. If this part is understood, let us restore this value in H dot dl is equal to 354 and we will use it in the part B. So moving to the part B, I have retained the coordinates and now we will evaluate curl of H of y as an approximation and we will find the quotient. So for this we need the area. Now we see that this is x direction, this is z direction, x and z, we have to find the area. We just know the points. If we know the points, we can find the length of each and every side of this rectangle, and then length into breadth gives us the area. Now from P1 to P2, y and z values are same, only x is varying, and that x is varying from 2 to 4, which means the number of units here is 2, which is upper limit minus lower limit 4 minus 2. So the delta x, change in x is from 2 to 4, which is 2 units. Similarly, the change in z is from 4 to 1, which is 3 units. Please remember, area can only be positive. So be careful while choosing the direction. Area cannot be negative. So the area we get here is 6 meters square. With this given area, we already have calculated H dot dl, which was 354 divided by 6, gives us 59 ampere per meter square. Since we are finding the component of curl in y with respect to y, we find the area x dot z. If it was component with respect to x, then we find the area y dot z and so on. So this is an approximation of curl on y. Moving forward to the last part, that is determine the curl of H with respect to y at the center. So what is this center? Geometrically it is possible to find out this center, which we shall do later. Let us try to find curl of H first. So this is the determinant form of curl of H, or we can also write it in the equation form which will be provided to us. So using that equation, we know the H is given by the equation shown here, 3z ax minus 2x cube az amperes per meter. Substituting the respective components here, our determinant will be like this. That is, hx component is 3z, hy component is not present because ay component is not present here. Hz component, which is accompanied by az component, is minus 2x cube. Expand the determinant mathematically. You know what to do. When you expand the determinant, if you want to find it with respect to y, then we don't have to expand the entire determinant. What we need is only the component of ay. So the determinant is dou by dou x of minus 2x cube minus dou by dou z of 3z. This is the determinant which we have to find, because we are finding curl of H only with respect to y component. That is, once you solve curl of H, you get it something into ax, something into ay, plus something into az. Out of which, what is curl of H of y? See, if we know this entire equation is H, then this 3z is called as H of x. Now, if this entire equation is curl of H, then the constant of this ay vector will be, or the variable of this ay vector will be called as curl of h within the brackets y. So that is why we are just finding the determinant, expanding the determinant only for the y1. So now what we have to do? We have to substitute the known values, that is for x and z. Which values we are supposed to substitute? Okay, so before that let us do the partial differentiation. Minus 2x cube differentiation with respect to x, it will be 3x square multiplied by minus 2, and 3z differentiation with respect to z will be 3. So the entire equation will be 3 2s are 6 and minus, so 6x square plus 3 will be the simplified equation. Now this is the equation at the center, curl of h of y at the center, but we want the value. So we have to substitute the value for x at the center. So what is that center value? See, throughout here we have the different values for x, which is 2, 4, 4 and 2. Now we understand that center of this and center of this and the center of this, these two lines, the x will be same. So here the center is 2, here the x value is 2, x value is 4, the center of this will be 3. Here the y value is 3, okay, and here also the y value is 3. So what will be the center of y value? Y will be at 3 only. Here the z value is 4 and z value is 1. The center of this will be 3.5. So these are the center coordinates. Kindly pause the video, take a moment to calculate these coordinates at the center. Please understand, it is the coordinate, it is not the distance. It is true that this point is 2 and this point is 4. Okay, the difference is 2 and half the difference is 1. That is to be added to the originating point. So we get it as 3. Here there is no difference. So the originating point itself is y component. Z component, originating point is 1, terminating point is 4. The difference is 3. Half the difference is 1.5. This 1.5 is to be added to the original point, which we get it as 2.5. Geometrically, please calculate these values. So this will be x, y and z value at the center. We are supposed to substitute these here. Fortunately for us, we just have to substitute the value of x, which is 3. And when we substitute that, we get the answer as 57 ampere per meter square. Now the question is, why is the unit ampere per meter square? Because the point form of Ampere circuital law, which is curl of h, gives us current density. The unit for current density is ampere per meter square. So this is the solution of the numerical, which is asked in 3 parts. I hope the solution is very clear to all. Let us move on to the next numerical task that was assigned to us. Let us verify the solution. So calculate the value of vector current density, which is J vector, which is nothing but given by curl of h. And we have the h vector given in all the 3 coordinate system. So then we know very well, we are aware that the formula will be given to us. The curl of h in all the 3 coordinate system, the formula will be given. We just have to substitute the given parameters, differentiate it accordingly and solve it to get the answer. So this kind of numericals are one of the easiest one, provided we are good with the partial differentiation and analytical skills. So there are 3 parts in this particular numerical. Let us solve it one by one. First, let us take the rectangular coordinates. Okay, the point given is 2, 3, 4, which is x, y, z. And the h value given to us, h equation given to us is something into ay and something into az, which means hx component is not present. The components that are present here are hy and hz only. Now why we have to check this first? Because this is our formula in the determinant form and in the equation form. If the component is not given, for example, hx component is not present here, then I don't have to evaluate the derivatives which has hx. So instead of finding 6 derivatives, it is enough if I find only 4 derivatives. So let us see it. So we will find the derivatives first. Okay, hx by dou of hx by dou y, which is 0 because hx component is not present. Hx with respect to z partial differentiation, once again hx is not present, so it will be 0. Hy with respect to x, this is hy, x square z. This is to be differentiated with respect to x, which we get it as 2xz because z is treated as constant for in a partial differentiation with respect to x. Dou hy divided by dou z. So this hy component is x square z. Okay, please understand, say there is no y here, but it is accompanied by ay vector, so this x square z becomes hy. So that is why we are substituting here. So this is how we differentiate. Similarly, the hz component is minus y square x. We have to take the sign into consideration. That one we have to differentiate with respect to x and differentiate with respect to y. So these are the partial derivative. Please take a moment to understand these partial derivatives. You can pause the video and rework this properly. I'm assuming the partial derivatives calculation is very clear to all the viewers. Only then proceed with this. Now that we have all the partial derivatives pre-calculated, just substitute it in the given equation, which is for ax we need dou hz by dou y. Dou hz by dou y is here, which is minus 2yx, minus dou hy by dou z. Dou hy by dou z is x square, but it is minus, so we put minus x square. And continuing the substitution, we get the equation like this. As we practice this and move forward, we can skip the steps and avoid putting zeros. But since this is for the first time we are doing it, all the steps are detailedly shown on the screen. We'll simplify the equation and we have to find this at 2, 3, 4. Once we have simplified the equations, for x substitute 2, for y substitute 3 and for z substitute 4. When you substitute this, you get the current density in amperes per meter square and the answer will be minus 16 ax plus 9 ay plus 16 az ampere per meter square. Please take a moment to solve this in your calculator. Moving to the second part of this particular numerical, which is in the cylindrical coordinate system. The points given are rho is 1.5, phi is 90 degree and z is 0.5. And the h vector is given here. Luckily for us, only the a rho component of the h vector is present. A phi component and a z components are not present. Which means in the given equation, what we have is only h rho component, h phi component and hz component is not present, which means these can be taken as 0. Now if these components are 0, their derivatives with respect to anything, partial derivatives with respect to anything will be 0. This is the first thing we have to note down. Now we'll take the equation of the curl. As we are aware that this equation will be provided to us, we have to use the equation as it is. Let us find these partial derivatives one by one. Okay? You can follow it in the circular symmetrical sequence, or you can take the derivative directly one by one in the formula and then substitute later. If you are confident enough, you can straight away do it in one step, which we do not recommend in the beginners. So now let us first calculate h rho with respect to phi. Okay, so this is h rho, which is 2 by rho cos 0.25. We calculate this, differentiate this with respect to phi. Differentiation of cos is minus sign, so we get this as the answer. Now what happens to the h rho with respect to z? We see that there is no z here, which means this becomes a constant. Partially derivative where the z variable is not there, this can be treated as constant and the derivative of a constant will be 0. This is for h rho. Okay, so we have got h rho by hz and we have got h rho by h phi. Now what we are supposed to calculate next? H phi, hz derivatives, but we know that h phi and hz are not present, so their respective derivative we don't have to calculate. It becomes 0. Please see here, this particular term here in the formula is rho h phi. So suppose if h phi component was given, multiply that by rho first, then do the differentiation. That is why this is shown in a different color, so that it can be a very clear indicator. So now we understood these 4 derivatives are 0. Okay. Now let us substitute it. So this is 0. The second term is also 0. For a phi, that both the terms are 0, we have calculated and substituted. And lastly, we have a 1 by rho here and substituted terms. Simplify the given vector. This is the equation. Find this j at the given point, which is 1.5, 90 degree, 0.5. So at 1.5, 90 degree, 0.5, substitute it. Get the answer from your calculator. Kindly verify. The last part of the numerical is with respect to the spherical coordinate system. The points given are 2, 30 degree, 20 degree. R, theta, phi for spherical coordinates. Okay, r, theta, phi, which means it will be AR, A theta and A phi vectors. And we see here we have the term only with respect to A theta, and that term will be H theta, which means HR term and H phi term is not present. These two terms will be 0. We have only H theta term. So if we have only H theta term, we have to find the derivative of H theta terms only. And the derivative of HR and H phi terms will be 0. So this is the equation. The highlighted ones are the derivatives which you are supposed to calculate. The all other derivatives become 0. Please take a moment to verify the equation. Now that we have understood the equation, let us find those two derivatives which are highlighted in amber. The first one is H theta multiplied by R. So H theta is 1 by sin theta. Multiply this by R, then differentiate with respect to R. So what happens? It is 1 by sin theta is constant now. Differentiation of R with respect to R will be 1. So we end up with 1 by sin theta. That is the answer for this. H theta with respect to phi, which means 1 by sin theta to be differentiated with respect to phi. Okay. Now we see that 1 by sin theta differentiated with respect to phi will be 0, because phi component is not present. It can be treated as constant and the derivative of a constant is 0. So we have only 1 by sin theta term, that is for this one, and we have 1 by R here. So all other terms here in the equation becomes 0. Only this term remains, which is 1 by R times 1 by sin theta with respect to A phi. So this is the equation for J. Now that we know the equation for J, we are supposed to find it out at the given point, which is at 2, 30 degree, 20 degree. Please understand, we are supposed to find theta, and this second term is theta, not the third term. Third term is phi in the cylindrical coordinate, in the spherical coordinate system. So the answer is 1, A phi ampere per meter square. I hope both the numericals are clear. Kindly revise these two numericals before watching the next video. Until then, goodbye.